that's it.
Okay.
All right.
Okay, so welcome back. Michael's already set up, and he's going to give us his second lecture on statistical methods. So whenever you're ready.
So welcome back, everyone. I hope you can hear me fine. The lecture notes are posted to the wiki page if you want to follow along. Today, we're going to get beyond the fundamentals we covered yesterday. I'll try to tell you about parameter estimation, confidence intervals, that kind of thing, which actually relate closely to the maximum likelihood method. And the least squares method, in my opinion, is really a derivative of the maximum likelihood method. So we'll cover these things and associated topics such as combining measurements. Okay, so to begin with point estimation, let's suppose you are the owner of a restaurant and you could only seat up to 19 people in your restaurant. And the expected number of people who come to eat are 19. So what's the distribution of the actual diners night after night? And of course, the answer is, well, it follows a Poisson distribution, which is what I'm showing you here in the middle of the page. So if you know that the mean lambda, the number of diners on average, is 16, then you can calculate the probability that people will be standing and waiting for a table, which is about 19%. But obviously, this depends on what the value of lambda is. So the real question is, how do you find expected number lambda? Right now, it may be kind of a stupid or a trivial question, but I'm trying to set up the following shift. Yesterday, when we talked about things like the Poisson, binomial, Gaussian distributions, and so on, and what a PDF is, and joint likelihoods and probabilities, and so on, we were taking the PDFs as given and asking about properties of the samplings, the variates that we derive or draw from those PDFs. So that's like the top part of this page here. But really, science doesn't work that way, right? We're not interested in a PDF that we know and then just randomly generating data. That'd be boring. Instead, we're getting the data that we get from the experiment or potentially from a simulation. And then we want to infer the values of parameters, especially those that have physics significant to us, right? So it's this bottom version here. It's this bottom version that is really what statistical inference is about. It's what makes science science, at least in a quantitative sense, okay? So what can we do with that set of numbers that we get, the data x sub I? Well, we can count them. We can calculate the mean. That's called the sample mean because it is based on the sample of x values that you have. You can calculate the variance. You can get the median, the point where half the values are above and half below. In all these cases, these various things that we're calculating are sample-based. They're based on the data values that you get. That there are two immediate consequences of that. First of all, it means that those values, the sample mean, the sample variance, whatever, those values are actually random values because they are functions of the data. That's really important. These are functions of the data in contrast to parameters, okay, that are sometimes fixed. The other thing is that in general, these kinds of quantities that are functions of the data and are meant to tell you something are known as a statistic. That's the technical word. So when people say, I don't have enough statistics, they don't really mean this. That's sort of sloppy language for saying I don't have enough events. When I say today a statistic, I'm specifically talking about something that you derive from the data, like the sample mean, for example. All right, so let's just consider a really simple example where we have those data. They come from a Poisson distribution. You know what that is. There's a single parameter lambda. And lambda in this case is unknown. Think about the guy who owns the restaurant and is worried about the mean number of people arriving at any given time. Okay, now we know for the Poisson distribution that the sample mean, that the parent mean, the true mean, equals lambda. So the obvious choice to make an estimate for the true mean is the sample mean. That's what this is here, all right? So the hat over the lambda says that it's an estimate or an estimator, not the true value, which does not have the hat. All right, so this sample mean is an example of an estimator of the Poisson parameter lambda. Now, there could be other ways of estimating lambda. That's what makes this interesting and challenging, but this would be sort of following your nose kind of approach. Now, even though that's really simple, we already have run into troubles, okay? First of all, the value of your estimator never is the right value. It never equals lambda, at least if this is taken from the real numbers, okay? There's always some sort of error of a stochastic nature. Secondly, if you repeat the estimate, you get a different set of data, you'll get a different value. So the value of the estimator is not unique, okay? Another problem, which is maybe a more algorithmic problem, is that sometimes as you increase the number of data that you're averaging over, you will expect that your estimator converges on the correct true value, but sometimes it doesn't. Sometimes you end up with a bias, B, which is bad. That's why it's the letter B. If you know, technically speaking, if you know what the bias is, you can just make a correction. But sometimes knowing what the bias is very hard to do. So people prefer an estimator that has no bias in it, that is unbiased. Okay, and then finally, as I already said, the choice of the estimator is not always unique. You have different choices. And of course, since you're a scientist, you want to make the best one, the best choice, find the best one. You have to figure out what that means. Okay, so let me give you a simple, hopefully fun example of different estimators for a different kind of problem, and we'll see how they compare. Let's say we're interested in the fraction of TASI students who are women, and there is some correct answer for what that fraction is. Of course, we'd all like to see it be 50%, but maybe it's not quite there yet. So P is the fraction, the true fraction of TASI students who are women, and we want to know what P is. So let's say that in this year's class, there are a certain number of students, 65, and a certain number of women, I don't know the number, M. How do I estimate P from the data? Well, this distribution is a binomial distribution. If you go back and look at what we had before, it turns out that the first estimator you would take is just the quotient, the fraction of women of all students who are women, P. So that's one estimator. There's a second estimator I could give you called the Run Statistic, all right? So let's suppose we order all of you students in some random unbiased way using, I don't know, let's say the last digits of your student ID numbers or something. And then we write out the sequence, males, females, males, females. This is totally random. There's no significance to the order here at all. Now you'll notice that there are little contiguous groups where the symbols M or F are the same. Each one of these is called a run. And for this example, there are 7 runs. You can count them up. So the number of runs depends on P, right? If P were 0 or close to 0, you just have all M's here. If P is close to 1, you'd have all F's. And in between, you'd have some maximum number of runs. So the expected number of runs is given by this formula. Don't worry about the formula itself. The point is that the number of runs does relate to P. So when you observe the number of runs, you can infer a value for P. All right, and this just tells you how to do that. And then finally, we could do something really dumb. We could just take the person in the middle and see whether that person is male or female and decide that it's either 0 or 1 if it's male or female. Okay, so which of these is the best? Here's a little toy Monte Carlo exercise. Estimator 1, that's M over N. If I do, I don't know, 10,000 examples, looks like this blue histogram. This is the runs statistic. It's a different statistic, not just M over N. The green histogram, and this is the silly one where I just look at the middle person. All right, so what I want you to see is that in the case of this one, it's a relatively narrow distribution, okay? The standard deviation is 0.618. Here, the standard deviation is a little bit larger, 0.0634. Sorry, I forgot a 0 here. And over here, it's really terrible. It's a 0.42. So the fact that we got a slightly more precise answer, a less dispersion in our answer with this estimator number 1 instead of estimator 2, except the estimator 2 is actually rather close, means that we would prefer estimator 1. It outperforms estimator 2 because we get a sharper answer, a narrower distribution here for the same number of, same amount of data. And this is terrible, as you would expect. Okay. Daniel's asking me, can I move the pointer? It's in the middle of the slide. And obscures the slide. Is that okay? I'm a little surprised that pointer makes any difference. Daniel, is that better?
For us, the pointer looks very big. So that's why he was complaining about
okay.
that. It's perfect now.
I apologize for that. I didn't realize that you would see that.
And you pushed it out of the screen, so don't worry about it.
Okay, great, thanks. And otherwise, the screen is okay, the slide is okay?
So far, so good.
All right, great. So let me continue then. All right, so the question is, which is the best estimator? In this case, we simply compared 3, and I argue that P quotient is the best estimator, but we haven't really gone into detail of what better is. And furthermore, we don't know if there is such a thing as a best estimator. Now, I could go on a diversion and explain things about efficiency and robustness, the Kramer-Rao bound. I'm not going to do that. Instead, we're going to tell you that the answer here is yes, there is a best estimator, and it's mathematically true that the best estimator is the one you get from the maximum likelihood method. So I'd like to turn now to the maximum likelihood method. And to set it up, I want to consider this really simple situation. Let's say we have a uniform distribution going between 0 and some upper bound A. And this is the black box is, that uniform distribution. And the little red lines are examples of data that might be drawn or come from that uniform distribution. Okay, and the mean, obviously, is in the middle because it's a uniform distribution. You don't have to calculate anything there. So I think it should be clear. Maybe I want to estimate the parameter A. It's not known to me. I want to know what A is. And one thing I can take advantage of is that as the mean of my data increase, the mean of my data increase, the mean of mu increases, and mu is really A over 2. So that A is about 2 times X mean. Okay, so this is just an example, and what I'm trying to say is that the sample mean gives me a way to estimate this parameter A, okay, by considering how my data observable X mean varies with A or with mu, which is a proxy for A. Let's consider something a little bit more complicated. All right, maybe that was certainly simple. Here's a different distribution with some data. And I've drawn for you a binomial distribution. That's just another kind of PDF, which depends on 2 parameters, alpha and beta. Okay, and you might not know it, but the true mean is equal to alpha over alpha plus beta. So I can go ahead and calculate the sample mean from the red lines, get a value, but how do I relate that to alpha and beta? If I want to know what alpha and beta are, how do I convert the mean of the red lines to alpha and beta? It's not so obvious. So let's figure this out. Let's suppose we already know what beta is, okay? And here's the data, and here's a guess for alpha. Well, the maximum of the curve that we get for that value of X, for alpha, ought to correspond to where a lot of the data are, because that's how it works, right? You'll get a lot of data where the PDF is high, and not so much data where the PDF is low. So you want to match the maximum of the curves where the data are densest. And you want to do that matching by varying alpha. Now, the probability, remember, for getting the joint probability for getting all these values is just the product of the individual probabilities for each value. That's because these are independent. These events are assumed to be independent. So I just take the product of them, right, the joint probability, is just the product of the individual probabilities. It factorizes, okay? So let's consider what happens then if I observe what happens to my calculated value for the joint probability. If I take a really low value for alpha, which means that the curve will peak at low values, a correct value for alpha, or a high value of alpha. Well, in these two cases, when you think about it, I'm getting a lot of small values from the, for the individual p sub j's. Here I'm also getting a lot of small values for the individual pj's. So these two are going to have p low. But when I have the correct value for PA, I might have a low value here or sort of low value there. But for the most part, I'm maximizing the subset of P sub j's, which are actually giving me a reasonable value of P. Okay, so what happens is that a curve of the joint probability versus alpha will have a maximum. And we can say that that maximum occurs at the correct value of alpha. That's kind of the idea. Now, it's a little bit of a misnomer or abuse of language to plot this as a probability, because a probability is a fixed thing. Instead, we define a likelihood function, L of alpha, which is equal to this probability, this joint probability, where alpha and beta are parametric dependencies, but here, the likelihood function we view as a function of alpha. Okay, and so the optimal value of alpha, the whole idea of the optimal value of alpha is the one which maximizes that function. Okay, so this would then be L of alpha on the vertical axis. Okay, now it's important. I want to make an important point that confuses a lot of people. Isn't the likelihood just a probability? Because after all, we went ahead and defined it as equal to the joint probability for observing the data given a parameter alpha. So the likelihood is a function of alpha giving the data, but that's literally equal to the probability of the data given the parameter alpha. So why isn't the likelihood a probability? Well, remember, any PDF, including a joint PDF, has to have an integral equal to 1. So if you were to integrate over all possible data of this probability, this joint probability here, it has to equal unity. It has to equal to 1. But L is a function of a parameter alpha. So if we want to integrate it, we're not going to integrate it over x. X is given to us. We're going to integrate it over the parameter alpha. And here, there's absolutely no reason why the integral of this function over alpha has to be equal to 1, right? So it does not satisfy the normalization condition for a PDF, and therefore it is not a probability. Okay, I hope that's clear. That's an important point. All right, so let's dig a little bit more directly into the maximum likelihood method. It was invented by Fisher back in the middle of the 20th century when he was hanging out as a graduate student, kind of pissed off about Bayesian statistics, and he said, I don't like that stuff. I'm going to invent a better method. I'm going to call it the maximum likelihood method. And yeah, he did it. Okay, so here's the joint probability function. Now is a function of a continuous PDF. Doesn't really make any difference. We define our likelihood, which is a function of the unknown parameter theta, as the product of these functions. And we toss the dx1, dx2, dx3, and so on away because they don't really play any role in the calculation. This is not a PDF for theta. Why? Because if we integrate over theta, we don't get unity. It cannot be viewed as a PDF. If, this is now a parenthetical thing, if we multiply the likelihood by a PDF, and if we normalize the product properly, that is then a PDF for theta. That's what Bayes' rule is about, but we're not doing that right now. Okay, so how do we maximize L? You all know this probably since the 3rd grade. You just differentiate with respect to the unknown parameter. You solve for the value of that parameter, which gives you 0. And that is, by definition, your maximum likelihood value or estimator for the unknown parameter theta. Okay, and of course, you don't want to really take the derivative of a really long product. Instead, you're clever, you take like a logarithm, you can stick a minus sign in front so that you minimize rather than maximize, and you can differentiate this relatively easily. All right, so very good question from Zhusheng Gan. How do we choose the proper form of PDF? That's absolutely crucial. If you have the wrong form of the PDF, the wrong function that you're fitting, you will get bad results. You'll get values for parameters, but the curve won't make sense. Other bad things will happen. Zhucheng, I actually give an explicit example of this later in the lecture. So I'm going to not give you more of an answer now and come back to this in a little while. But it's a crucial question, so I'm glad you asked it. All right, here's a one-page example. If you wanted to know what is the best value for lambda here, this is the Poisson distribution, sorry, the exponential distribution. Lambda is 1 over the mean of x, turns out. So the question is, should you take 1 over the mean of x for lambda, or should you take the average of 1 over the extra x values? Okay, which one is the right one to do? You could try to guess, or you could follow Fisher's example and do a maximum likelihood calculation. Here it is, just the sum of logs of this expression. Okay, I just did a little bit of elementary mathematics for you. Here we are with the correct closed form expression. We take a derivative with respect to lambda. Everybody can do that. You set it equal to 0. And then in the end, you find out that the maximum likelihood estimator for lambda is indeed this guy and not that guy. Okay, so that's how it works. Very simple. All right, now I want to switch gears slightly, not too much actually, and talk about intervals, confidence intervals. The estimator is a stochastic variable, right? I emphasized that before. You can see it in this expression here. It's a sum over the data. The data are random, therefore this guy is random. Question is, how much is the value of lambda susceptible to fluctuations in the data? Is it very susceptible, so the value is jumping all over the place, or do you always pretty much get the same value? Obviously, the latter case would be better. And so this brings us to estimating or talking about an interval which sort of bounds the fluctuations that we expect in our estimator lambda or whatever it may be. Okay. So the point estimate, let me remind you, corresponds to a single value. The temperature in this room, I estimate to be 69.2 degrees Fahrenheit, period. An interval estimate gives you a range of values where you say, well, the temperature of the room lies in the range between, say, 68.9, 69.4, with a certain confidence level, with a certain probability, let's say 68%. And sometimes we write it this way as a central value plus or minus some value. Okay, so here we have a PDF for the measured value. Here's the true. And the idea is that the measured value will be randomly fluctuating around the true value in some way like this. Question from Daniel. Isn't the likelihood indeed a probability, just not the probability we're interested in? Wouldn't it be the probability in the technical sense of seeing the data you saw, given the distribution you were guessing? Daniel, no, the answer is definitely no. The likelihood is never a probability. I tried to show that because the true parameter, lambda or alpha, whatever it is not a random variable. There's a one unique true value that we sort of assume that's true. So you can't really integrate over true values. That doesn't make sense for this kind of treatment. And even if you go over to Bayesian statistics, you can use the likelihood in order to build a PDF for the parameter, but you need other ingredients. The likelihood by itself does not suffice. So just to be clear, in categorical, the likelihood is not a probability in any way. Okay, let me, why is it plus or minus 0.3? Probably because I can't do arithmetic. Yeah, no, you didn't, Ma. Looks like I made a mistake, typo. Okay, so yeah, this should be a 5. Sorry about that. All right, so the question is, now you make a measurement. So here's the measured value in the middle. And then I open up an interval. I happen to know that if I open up this interval, whatever it is, it has a lower value, it has an upper value. And the idea is that it will encompass the true value 68% of the time, okay? You could use something other than 68%, but 68% is the convention. All right. So the important statement here is that the true value is wherever it is. We're trying to find out where the true value is. We don't know where it is. Otherwise, we wouldn't bother to measure it. The true value happens randomly to fall in this band 68% of the time. These two things are the data, or they are functions of the data in our understanding of the measurement process. And it could be, like in this case, that the true value actually lands outside of this interval that we specify at 68%. Okay, so the interval is not guaranteed to include the true value. In order to do that, we'd have to have 100% confidence level, and that would include all possible outcomes. That means it would go up to positive infinity for the temperature and down to 0, which is a useless statement. Okay. I'm going to move a little bit faster because there are other good things to talk about. This is sort of the same thing. Alpha is this coverage probability, okay? So for 68%, it's 16%, 32%. And the point is that if we would take the measurement many times, we would find that some of the time, the true value is not falling inside of our confidence level. Okay, so here's an example where I threw 100 random numbers, and indeed, sometimes the values that I get are outside the, this case, 95% confidence level interval. And that's just the way statistics works. That's the way it is. There's nothing you can do about that. Sometimes you're lucky, sometimes you're unlucky. In any case, this is how it works out. And you have to keep this in mind, because this is doing a measurement 100 different times, but maybe your first time works out to be this guy. And so you're unlucky because you're far from the true value just by random fluctuations. Okay. Now, I hope you can have a kind of intuition that a narrow PDF for theta hat for your estimator is a good thing. In other words, if your estimator theta hat doesn't jump around very much, then your statement about where the true value is likely to be is more precise, is tighter, right? So if I go back to this, this is precise at the 0.2 or 0.3 degree level. So the true value is going to be, between 68 and 70, something like that. If, however, this was much narrower and only constrained between 69 and 69.2, we'd have a better measurement and we'd make a more precise or a tighter statement about the true value of the temperature. Okay, so we want a PDF for theta hat to be narrow. Okay, and we can address this using the maximum likelihood method in a very nice way. Okay, so we like to minimize the negative log likelihood. That's this thing on the left. And this is an ordinary Taylor's expansion. This is just the minimum. It's a constant, does not really interest us. Sorry, can't spell. Minimum. This term here is 0. Why is it 0? Because that's how we define the value of our estimator in the first place, is we want the minimum of this function, so the first derivative vanishes there. And then that leaves us this quadratic or second order term for theta. Okay? So this second term is the curvature, all right? Maybe to make a little bit of a picture so it's not just mathematical equations, if we're drawing as a function of theta hat, the negative log likelihood, then there's a minimum. That's our theta hat ML. And how narrow this is, right? this term here, it's a parabola, right? We're just writing the equation of a parabola. That then gives us the second order term here, gives us the curvature. How sharp is this? Is it broad like that? Or is it narrow like this? And of course, narrow is what we would prefer. Okay. When the curvature is small, then the parameter is sharp, like the dotted line here. When the curvature is large, then the parabola is broad, and that means we have less constraint on the truth because the fluctuations of our estimator are large. Okay. So here's just a picture. It also turns out, again, we don't have time to prove this, but this 68% confidence level, confidence interval is actually determined by where on the parabola the negative log likelihood rises from its minimum value to its minimum value plus 1/2. Okay, so this interval here determines the confidence interval. All right, so we have a question from Xu Shenggang. Why do we expand over log L than L? Because it's log L, which has a parabolic form like this. You could try to, it's a good question actually, you could try to take the derivative of the likelihood itself, but it doesn't work out very well and it's not instructive, whereas this is instructive. And also I'll show you something else really nice about this construction in a couple of minutes. And going back to page 33, capital N is the, yes, is the number of data points, Xiaolongli. Okay, this is the number of data in the set that we're working with, X sub I. Okay, all right. So in fact, you're welcome. So having now given you a sketch of the basic idea of maximum likelihood method, I now want to talk about least squares estimate because it's closely related. Okay, now, you may know that many random variables are normally distributed. That's why we call it the normal distribution. And so it's worth taking a close look now at the maximum likelihood when the underlying PDF is a Gaussian. Okay, so Gaussian, you know the form. Here's the likelihood. It's really the negative log likelihood. Sorry for the ambiguity there. For a Gaussian. And let's say we're really interested in the mean of the Gaussian, the position in our calculation. In that case, we can kind of throw away this term, and we can even throw away that term, because when we take derivatives and things like that, they won't play any role, they'll just go away, okay? So this term here is the one of interest for a Gaussian. And in fact, we might as well isolate it, maybe without the 1/2, and call it something else. We're going to call it chi-squared. And I want you to notice that I talked about standardized variables twice yesterday. It's the random variable minus the mean for the random variable divided by the standard deviation of the random variable. So in a way, this is like a zi squared, where z was a random variable for a Gaussian. Okay, now if you just look at this for a second, if we're minimizing the left-hand side with respect to mu, the mean, then we're also minimizing chi-squared. Okay, we're minimizing this quantity in blue here. Okay, so the least squares estimator, which comes from minimizing chi-squared, coincides with the estimator for maximum likelihood, which coincides, you can do the calculation and see, coincides with the sample mean, right? So this is all very neat and tidy. For a Gaussian, everything kind of falls together and converges on the same answer. But for other kinds of distributions, it's not necessarily true. Okay. So the least squares you can think of as being the maximum likelihood method where the underlying PDF is a Gaussian. Okay. Now there's some variations we can do. In this case, we said there's just a single common standard deviation, but you can still continue to do this exercise when you allow each individual term to come from a Gaussian of a different width. That's what I've done here in red. Or, well, I'll come to that in a second. Let me answer Hongkai Liu's question. On page 37 is the log L. Yes, that's what negative log likelihood stands for. Yeah. Okay. Now, we can also generalize this in the following way. This is the same expression. I just write it in the silly way because what I really want to do is to construct a matrix, which is the inverse of the covariance matrix. And then I want a column vector here and a row vector so that in the end, I can write my chi-squared in this compact form. Okay, this may seem like just a game with notation, but the main thing I've done is I've introduced the inverse of the covariance matrix, which is valid even if my covariance matrix is not diagonal. Okay, so in other words, if I have off-diagonal elements, which if you recall from yesterday corresponds to covariances, then I can still use the same formula for defining my chi-squared. So now we're doing something that we couldn't do so easily, or really not at all, with the maximum likelihood method. We're incorporating crucial information about covariances, the way the different x's might not be independent. There may be correlations between them, non-zero correlations, even negative ones. By using this least squares method and working with the full covariance matrix, we handily, in a nice, elegant way, take this into account. Okay, and then finally, we can also generalize this so that instead of simply looking for a mean parameter of the Gaussian, we can basically take any function that depends on x and some parameter by minimizing chi-squared with respect to that unknown parameter. Again, the chi-squared gives us a nice way of finding a minimum. So Adrian's asking a question. He says, or he asks, is this the same kind of covariance matrix that experiments might calculate for bin data? Yes, absolutely, Adrian. That's the whole point. That's, I'm glad you picked up on that. That's what this is all about. Okay, excellent. Okay, so last thing I want to point out is if we go back to that Taylor's expansion that I wrote before, and then I multiply by 2, then it turns out that I can rewrite that Taylor's expansion as nothing else but some uninteresting irrelevant constant plus chi-squared. Okay, so the chi-squared actually also relates to the minimum of the negative log likelihood, or the negative log likelihood is related to chi-squared. They're the same thing. You're plotting versus some theta hat. In both cases, you get an upward going parabola, and you can understand the fluctuations in the value of your unknown parameter just by the same construction of looking at the curvature at the bottom of the parabola, taking a second derivative. Anybody can do that. Okay, so now armed with the least squares method, I'd like to talk about curve fitting. Here's some data. It's fake data. There's a curve going through it. It's actually a straight line, but we all call that a curve, of course. And I want to tell you how to fit things. So Pranjal, I'm not sure your question about using maximum likelihood. Are you asking about using maximum likelihood for determining the width here? Or are you talking about using it for curve fitting versus least squares? So maximum likelihood is actually, I didn't emphasize this, but you can prove that it is the best way of constructing an estimator. It can also be the most difficult way of constructing an estimator, in practical sense. Whereas the least squares is often only an epsilon worse, and it is much more straightforward and has intuitive pictures associated with it that just don't apply to a maximum likelihood. So there are many situations where using a maximum likelihood is, using a golden diamond studded knife to spread your butter in the morning. You don't need it. It's overkill. It doesn't fit. It's inappropriate, right? Some problems are just fine with the least squares. But for other things, you definitely want to use a maximum likelihood. So for example, if you don't want to bin your data, then you must use a maximum likelihood. So, all right. Let me talk a lot about curving, fitting curves, I should say. Here's a bunch of data that I made up. There's a curve that goes through the data. I want to know, how do I get the best curve? How do I fit the curve to the data? Okay, a curve that is like this is a crappy curve. A curve that goes like this is also kind of a lousy curve. That black one is a good one. How do I find the best curve that describes this linear relationship? Okay, so a common way is using the chi-squared function. You can use the maximum likelihood, but it's often difficult. Let me pause to answer Edward's question. He's asking, is a good question. What happens when the maximum likelihood is not unique? You know, is not unimodal, I think is the buzzword for that. If it's bimodal, then normally you rely on whichever of the two has a higher peak. So Edward, if it turns out that both peaks are the same because you have a degeneracy, then at that point you have to report both answers as being equally valid for the data, given the data. And this happens all the time in neutrino physics when people look at CP violating quantities, or when they look at some of the angles in the PMNS matrix. That's a constant problem, because when you have quantities that are squared, obviously you cannot differentiate positive and negative at that point. Okay, I won't be worrying about that, but it is actually quite a good question to ask. All right, going back to the fit, here's my ansatz for a chi-squared. It depends on a single parameter lambda. And I'm going to minimize this function with respect to lambda to get the best value of lambda. Okay, so this is basically all I'm doing. I just take a derivative. Again, this is easy. Let's go ahead and do the case for a linear function. This is a straight line, right? Notice that the function is linear in these two unknown coefficients, a and b. So I write my chi-squared more explicitly this way. I want to minimize simultaneously with respect to a and b. So this gives me sufficient information to uniquely determine a and b. In the interest of time, I'm going to skip over the details, the calculation details. This W is just 1 over sigma squared. This is a linear algebra problem. You can solve it. Here are the solutions. And this is maybe looks a little bit intricate or innate when you see it, but it's actually pretty elegant and very pretty, I would say, because you can obtain, without any kind of search or jumping around or random trials or complicated MCMC algorithms, you get a unique calculable answer for the intercept and for the slope of your line. You just calculate it from the data and out comes the result. Okay, if you want to see an extended discussion of this, this is the most common fit in the world. You can see a very nice book by Bevington for more details. Okay. Now, an even simpler problem would be when y is just proportional to x, and we want to determine the proportionality and the uncertainty on the proportionality, or this is just comes from calculating the second derivative at the minimum. Well, here's some data, 1, 2, 3, 4, 5 points. Calculation tells me that A is 0.502. I would say that that blue line matches the points rather well. Of course, they're a little bit above, a little bit below, but that's in the nature of random data. That's the way it should be. It looks okay. How sensitive is the chi-squared function to the value of A, right? Could I take 0.702? Could I take 0.499? How do I know? I see how much chi-squared is going to change, right? If chi-squared jumps from its minimum to some gigantic value, chi-squared min plus 92, that's bad. That means that value over here is not allowed, okay? So let's vary A between some plausible range. That's just what these different dashed lines are, correspond to this range of A values. And I think it's pretty clear some are better than others, right? This lower line might really hit that term, but it's so far away from these guys no one would think that that's a good fit. Okay. So here's chi-squared versus A, calculated explicitly for that range between 44 and 0.66. There's a clear minimum close to 0.5. Well, of course, because we got 502. And graphically, if you look at chi-squared min and chi-squared min plus 1, here, this range here back and forth, that kind of looks like plus or minus 0.03, okay, graphically speaking. All right, so if you complete the calculation and calculate the errors, then indeed we get 0.027 and the chi-squared value is 3.25. Is this a good fit, right? This is a really important question. You do a fit, you look at the data, you visualize the data like this, you draw the fit. Is it a good fit? How do you know? Well, here I took the same data points and I shrunk the data down really low. I just imagined that all these values were measured in a more precise way. As a consequence, the uncertainty on A goes down because I have more precise data going in. I'm going to get a better, more precise value for A. My chi-squared parabola is going to be super narrow in this case. And I get a really high value for chi-squared. If I take the other extreme and blow up the error bars, again, the central value doesn't change because these central values have not changed, but I get a bigger uncertainty and I get a really low value of chi-squared, 0.64. So maybe the low chi-squared says that this is a great fit, right? So here's a summary. Central values are the same. The uncertainty on A changes a lot, and together with that, so do the values for chi-squared. Are they all equally good? If not, which is the best one? So here's a plot of the distribution of chi-squared we expect for this problem when there are 4 degrees of freedom, because there are 5 points. So chi-squared is a statistic. It is a random variable that depends on the data. So if you get a bunch of random data and you calculate chi-squared, you're going to get a random value for chi-squared. You might get 22, you might get 10 to the minus 6, but what you would expect to get in this case is about 4. Okay, and you can see that from the curve. This is a PDF for chi-squared itself. And yeah, roughly speaking, the kind of central region here is about there, around 4. So remember, the 3 values that we got were here. So 0.64 is down here. And 26.5 is way, way, way. I can't even draw a 26.5 on this graph. So if we go back to yesterday's discussion with p-values, the p-value for this guy, how extreme is 0.64? It's kind of extreme. And how extreme is 26.5? It's really extreme. The chance to get 26.5 or larger just from random fluctuations must be 10 to the minus 4 or something. It's ridiculous. But 3.25 right here, that's kind of right in the middle, even near the peak of the distribution. So that seems like a valid expected value for chi-squared. Okay. So when chi-squared is near the center of the distribution, it occurs at around nu, the fit is good. If chi-squared is too small, then maybe the uncertainties are too large. Maybe, there's been a problem in estimating the errors. And if chi-squared is too large, then you should doubt the fit. Perhaps the uncertainties are small, or maybe you have the wrong model. Okay, so somebody asked earlier about the model. Let me give you an example now of what that looks like. This is a different set of data. The same calculation for A gives me this value. And again, I get some, kind of annoying value for chi-squared. It tells me this is no way a good fit. And you can see why. Because if I just say that y equals ax, then it doesn't really allow to fit these 2 guys on the one hand and these 2 guys on the other with a line that goes through. But you can see that if I were to allow a non-zero intercept like this, maybe it would work out okay. Okay, so let's go ahead and do that. Let's add a second parameter. Let's do a chi-squared minimization. We get a different value for A. We now get a non-zero value for the intercept. We get a reasonable value for chi-squared. And indeed, the fit itself looks good. Okay, so here's an example where before we got a bad value for chi-squared, not because there's something wrong with the data, but because the model that we chose was the wrong model, mathematical model. We used the wrong function. Okay. So since this brought us success, why not just add a quadratic term? Maybe there's a little bit of a quadratic term or a cubic term or a quintic term. Let's go ahead and go all the way to the fourth order in X. Well, we have 5 points and 5 unknowns. So that's exactly enough to give you a line that literally goes through every single point successfully. This is awesome. Okay, this is the best model ever, right? Because we get a chi-squared of 0 and the curve goes through every single point. What's wrong with this? What's wrong with this is that we've overfit. It's bad. We have not accounted for the fact that these values are random, or we've ignored the fact that they're random and they're going to fluctuate. Okay, so the model, this is the model here, has accommodated the random fluctuations of the data, and that's not the idea of any model. The model should somehow ignore the randomness and extract the essential tendencies, you know, like here. Okay, so you can even show that that model will tend to give you an inferior, a poor description of the data. Here's an example where I generated another 5 points consistent with the first 5, but you can see that those new 5 data are better consistent with the original dash line than with this crazy line, curvy line, which was fourth order in X. Okay, so overfitting is bad. There's sometimes a temptation for people to just add lots of extra stuff because they want their function to be flexible. But if you carry it too far, then you shoot yourself in the foot and you get wrong results. All right, last thing about chi-squareds I want to say is that those 2 examples were linear in the unknown parameters, A and B or whatever. That makes a minimization very easy, but if you have a more complicated problem, this is slightly more complicated, it's again an exponential, when you carry out the minimization of chi-squared, here it is, ultimately you are led to a equation that is transcendental, that has no simple closed form for lambda. You cannot solve that from lambda except using numerical methods. Okay, so in the case of this function, I went ahead and I minimized chi-squared, so I figured out what is the best value for lambda. And then when I use that best value, it very nicely passes through the points and gives me what looks like a good fit. All right, so I have a question from Koyue Liang. Sorry that I mispronounced your name, forgive me. How to determine the least parameter in the model? If you mean the fewest parameters in the model, that's actually a difficult question to answer. And people debate and argue about this. Let's say it's at the forefront of statistical data analysis in the sciences. So one way to do this is to begin with one parameter, maybe knowing that this is going to be a bad model, adding a second parameter and see how much the chi-squared decreases. So if this one parameter gives you a chi-squared of 78, for 5 degrees of freedom, it's terrible. Then you add the second one, maybe you got to 12. That's a good, big improvement. Maybe you add the third one and now you get to 4. That's about what you expect. If this one then gives you 3.95 and this gives you 3.92, this decrease in the chi-squared is so small that you say that the additional degrees of freedom are not really helping you at all, okay? And so you would cut it off in this example after adding 3 parameters. All right, so that's known as the Bayesian information criteria or F-test. It's often called an F-test. There's also Ikaki information criteria. So there are different rules that people use to have a model that's flexible enough, but not too flexible. Okay, next question. For periodic functions, the Taylor's expansion is not applicable. This is true, but we're not talking about periodic functions. We're talking about things that have a unique minimum. Both the chi-squared and the negative log likelihood are not periodic in the arguments. And then why did we suppose n equals 4 for 5 data parameters? That's very good. I didn't explain that. You can see here, for example, that there are 5 data points. And I'm actually, this is the wrong example. Let me go back to this other one. Yeah. So there are 5 data points. But we are determining one parameter in our minimization procedure for this example on page 54. So the rule is you subtract the number of parameters from the number of points, and you get 4 degrees of freedom. And that's really the true meaning of nu when we're talking about a chi-squared distribution. Okay. So the points, the data points minus the number of parameters is the number of degrees of freedom, and that's what chi-squared corresponds to. Okay. From Pranjal, you've heard that people calculate chi-squared per degree of freedom to find the number of optimal parameters. I would not advocate for that. No, that does not sound valid to me. Maybe there is a technique that I'm unaware of. I don't know everything. But I don't, it's hard for me to think of that as being valid. There's also a technique used by the particle data group where they use the chi-squared function to estimate corrections to errors and things like that. But I wouldn't advocate for that either. Okay. All right, so where are we now? We are done with this. And combining measurements. So Andre, I want to ask you, I have really 2 sections that I wanted to go through. However, the second one I can postpone until tomorrow without a problem. Would you mind, or would the organizers mind very much if I spoke for another lectured for another 5 minutes?
Oh, no, I think you have even more time. You have 15 minutes, right?
Yeah, you're good until 15 past the hour.
Oh, I see. I thought I was supposed to pause now in order to allow general questions and answers, but there've been great questions today. So if you don't mind my going ahead, then I'll be happy to go ahead because I want to talk about combining.
You own 15 minutes.
Ah, great. All right, I'm going to share it with everybody then. All right, here we go. Talking about combining measurement. So many of you, I hope, have seen this picture before. It is the picture from the announcement of the discovery of the Higgs boson. I know all you guys really care mainly about neutrinos, but this is a wonderful moment for all of particle physics. Why am I showing this picture? Because I'm going to talk about the Higgs boson as an example of combining measurements. What are we going to combine? Well, first of all, we can measure the Higgs boson mass through the channel, Higgs decaying to 4 leptons. Okay, and so we've got right here a signal from Atlas. We've got from here a signal from CMS. Because I'm on the CMS collaboration, I think our signal's nicer than theirs. But if anybody out there's on Atlas, I apologize. I don't mean to disrespect Atlas. In any case, these 2 data sets, these 2 peaks, give us measurements of the Higgs mass. We want to combine them. But it turns out there's a second channel, Higgs to gamma gamma, which gives us actually even better measurements of the Higgs mass. So here you go. Here's a really nice Atlas measurement of Higgs mass. And here's a decent measurement of the Higgs mass from CMS. So we actually have 4 measurements, 2 in H to 4 leptons and 2 to H to gamma gamma. And because you're theorists, you know you don't care about the individual measurements. You want to know what is the most precise value for the Higgs mass, taking all the data into account. Okay, imagine one day we're combining measurements of the mass eigenstates of neutrinos. That would be really cool. All right, so this is just a summary of the 4 data. This is a little bit dated. This is from ATEV, doesn't matter. The best value is obviously whatever we get when we combine these. One thing you could do is just add them up and divide by 4. That's a combined value, but it's not the best combined value. The way we're going to combine the values is using a least squared method to combine them. This is equivalent to something known as the best linear, unbiased estimator for a combined measurement. All right, this is by far the most common and most successful method for combining measurements, and it's equivalent to doing a least squares fit. So we have 4 measurements of the mass m. We're going to call those y sub I with uncertainties sigma sub I. And we're not, for now, we're going to ignore correlations that might be there, okay? So our function, when you think about it, is extremely simple. It's just a level function, right? If we just plot the 4 values, 1, 2, 3, 4, we just want to plot, find the line, the horizontal line with no slope that minimizes the chi-squared, you know, with respect to changes in this direction. All right, so it's a level function. Here it is, it's just a parameter sitting there by itself. So it's really, really easy to calculate the least squares estimator for this. Here's the formula. It's a formula for a weighted average where the weights are given by 1 over sigma j squared, okay? The variance on that parameter, again, coming from the curvature of the chi-squared function, turns out just to be the sum of the inverse variances of individual measurements, okay? So that means the more measurements you have, the more precise this is. It also means the smaller that these guys are, the more precise the result is. Makes sense. All right, so for those data, here's what the formulas give. All right, that's the answer to a least squares minimization. And here's the graph, which of course corresponds to the values. Now chi-squared is 8.8. How many degrees of freedom do we have? We have 3. So that's not so good, is it? 8.8 is a bit high when you have 3 degrees of freedom. So what do we need to do? We need to look at the data, okay? So 8.8 is out here. And this is the chi-squared function for 3 degrees of freedom. So the probability, in fact, for getting 8.8 or higher is only 3%. So for example, of course, Atlas and CMS looked at this very careful. Here is the data for the gamma-gamma channel. The black curve is the combined result. The red curve is Atlas. The blue curve is CMS. By the way, you can see right here from the narrowness of the parabola that for this specific measurement at this specific time, CMS had a better measurement than Atlas. Not always that true, of course. Is it okay? Not really. The separation from these 2 minima is really high, right? This is delta chi-squared equals 1. That's like plus or minus 1 sigma. This is delta chi-squared equals 2. That's plus or minus equals 4. This plus or minus 2 sigma. So these data don't really look too compatible. On the other hand, you can compare Atlas and CMS just on the overall picture. And here, things look great. So Atlas and CMS decided to publish, but we were nervous about it. And there's a lot of attention paid in subsequent data analyses to clean this up and figure out what's going on, okay? So what about correlated uncertainties? Well, remember the chi-squared that we had back here was really simple, right? But I also taught you, okay, went by fast, but I taught you how to generalize this to use the inverse covariance matrix, in which case we can take the correlations into account. All right, so if, and in fact, when those combinations are done, the experts who do the combination most definitely take correlations into account. And so you just have to build a covariance matrix and use this version of the formula to minimize, okay? One thing I want to make sure people don't miss is the fact that the calculated value, the central value for M, will depend on the covariances, right? This is a set of linear equations. If you're changing the coefficients, the answer will be different in the end. And you shouldn't forget that. Okay. All right. Since I have maybe 2 more minutes, let me just make one last point. Fitting functions is nice. We just fit a level function, we fit straight lines. We did a couple of things quickly, but there are situations where maybe it's not the best thing. So here's some data, and I believe maybe they're falling off exponentially. And I need to know, I really need to know, what is the value when x is 3.51 right here? What is the correct value for this data? What should y be when x is 3.51? Well, the obvious thing to do is to say, well, I'm going to guess that this is an exponential function. I perform a least squares fit, and then I evaluate this black line, that's the fitted line, at the value 3.51, and I get 35.2 as a result. Okay, so that's that black point there. Is that a good idea? I mean, we've got these points, they're all kind of low compared to the black dot. Maybe people don't like that so much. Maybe we should fit a linear function. Maybe we should fit something else. Pranjan, I'm going to come to your question in a second, okay? So I don't mean to ignore you. All right, so there's another way of doing this called non-parametric regression. The idea is, let's not do any fitting. Forget about maximum likelihood. Forget about chi-squared or least squares. Don't even use an analytical function. I'm going to just go ahead and take a local average of, say, 4 or 5 or 3 points and use that local average as my estimate. Okay, so this is what we do here. This is known as the KNN, or K nearest neighbors. You just take a running average as you go from left to right. You just have a little window that you take an average, and as you move that window left and right, the average will change. Okay, so if we do that, we get 96.5, 26.5, that's about here. And that looks much more reasonable than the 30-something that we had before. Okay, so here's a direct comparison of the smooth curve, which is the exponential that we fitted with using these squares, and the KNN that we just constructed. Now, here's also, so you could ask, which one is better? Well, it depends. If you believe the small depression here in the data is a real effect, then you don't like the fit because it doesn't take that into account. If you think it's a fluctuation, then you don't like the KNN because it's sort of overfitting here and describing a fluctuation rather than a real effect. So one way to see what happens is to generate many different data sets like this one and consistent with this one, and do the KNN and do the fit many times. So this gives you, I think, 50 or 40 or so versions of the fit. So you get a nice narrow band. And this gives you 40 or 50 versions of the KNN, and it gives you a wider band. The reason why it's wider is because it's more flexible. It's not really a fit, but it is not taking into the kind of strict assumptions that you're making when you declare that the data are exponentially decaying. Okay, so there are some advantages and disadvantages to this. Non-parametric methods like K nearest neighbors are unbiased. You don't assume anything about which function to use, and you can show they reduce to zero by the bias to zero, but you have a larger variance, right? The spread here, that's the variance, that spread is definitely bigger than over here. Parametric methods have the advantage that they bring in external knowledge. Maybe you really know that it's an exponential or a linear function. If it's true, then you reduce the variance. But if it's incorrect, then your assumed function will bias the result, okay? You can sometimes use goodness of fit tests like we showed before to check for wrong functional forms, but not always. And this sort of, do I want bias? Yes or no. Do I want a smaller variance? Yes or no. You cannot have both. And so this is a typical trade-off between bias and variance that is ubiquitous, is at the core of all quantitative data analysis. So Pranjal, let me come to your question. Sorry to be making you wait for so long. No, there's not really an estimator that tells you when it's bad to combine data. However, I mean, it's actually a crucial question that you asked. However, obviously, because I focused on it, the chi-squared for the combination, if it's really too large, then you feel like maybe the data don't correspond to a unique value. And you have to speculate then that one or more of the data input are wrong. You can do some trimming You can throw outliers away. People play all kinds of games with this. And in fact, I put a lot of slides in the backup slides, and there's a whole section there about what to do about trimming data. Okay. From Matteo, is there a likelihood method to combine the data? No, not that I've ever seen. The problem is it doesn't lend itself to that. The only way you could set up a maximum likelihood that combines data is by using a Gaussian PDF for the input data. And when you do that, it's literally exactly mathematically the same as least squares. So why do it? From Curtis, is the last bit there essentially bootstrap? No, Curtis, bootstrap is something else. Unfortunately, because I'm only giving 3 lectures, I had to cut out my section on how to generate distributions and the bootstrap. Just to explain for those who might not know, bootstrap would correspond to, let me go back to this guy, sorry. Hold on. It's a nice question, I like the question. So bootstrap corresponds to, for example, leaving out a few of these points and then refitting, and then leaving out a different set of points and fitting again, and looking at the ensemble of different fits that you get to give you a sense of the uncertainty, much like I did here with this guy. This is not a bootstrap, but it's similar in spirit to a bootstrap. From QUA, Young, can we use a piecewise linear fitting there? There won't be a systematic bias in the model. Yes, you can. However, suppose what you're after is, I mean, maybe this is a lifetime for some decay of a metastable state. Let's say you're looking at heavy neutrinos on a decay with a lifetime or something like that. Then you want to use an exponential, even if you could use something else like a piecewise continuous data set. So there's no hard and fast rule about using analytical functions only or using non-parametric or piecewise continuous functions only. It really depends on what's best for the problem at hand. From Zhu Shangan, does it make sense to extend the fitting function to a range far outside the data set? That's a really interesting question. Sometimes you have to, right? Sometimes you have, let's see, let me insert a page like I did yesterday. Maybe you have, you want to know the intercept here, and your data are like this because you're measuring something as a function of temperature and you can't go to 0. And so you have to extrapolate back here to get the intercept. So yes, you can do that, but it turns out that because of the extrapolation, your uncertainty on this value, right, your confidence interval could end up being very large, even though if you could evaluate the same quantity, the vertical quantity inside of here, it would be small. So extrapolation usually magnifies uncertainties. All right, from Xiaolong, Lee, how to handle a case when the lower and upper uncertainties are different. That's actually not a problem. If you have, again, I didn't take time to go over this, but it's not unusual, especially in neutrino physics. Let me try to draw this carefully, sorry. It's not unusual to deal with quantities which do not give you a perfectly parabolic symmetric parabola. And so if you find your minimum here, to give you your lambda hat, and then you draw a line across, you'll see right away that the interval on the upper side and the lower side are not the same, right? This one's bigger than this one. In that case, you would say lambda hat is, I don't know, 29 plus 4 minus 3. And that's the convention for indicating what you do when the confidence interval is asymmetric like this. So from Pranjal, if we add negative log likelihood from 2 data, then minimize it, isn't that likelihood method for combined data, following Matteo's question? I don't think so. I don't think so. I might be missing something, but when we are talking about data points like this, you have to understand that in a way, this represents a Gaussian, right? So the input to any calculation when you have individual measurements like this means that you have, for whatever quantity you're trying to measure, M, you have a Gaussian for all the different measurements, 3, 4, 5, 6 measurements. This is for combining data, and you're trying to combine all of these. I don't see an easy or good way to write a maximum likelihood for this problem, except as a product of Gaussians. And as I said before, that amounts to the likelihood. So, I mean, I will be in the office hours this afternoon, so I'd be happy to go into more detail on this question since a couple of you brought it up. Do the values of delta chi-squared that correspond to, this from Nina, to 1 over 1 sigma and 2 sigma ranges depend on the number of years of freedom? Yes, absolutely. Actually, no, sorry, it does not, but it does depend on the number of dimensionality of your data. So I've only talked about one-dimensional data here, but as we said yesterday, sometimes you have 2 or 3, and then what are the right chi-squared contours becomes more complicated. Okay. From Ma Young, how to sum the uncertainties from different sources. Okay, so I glossed over this. Normally, what you would do is if the 0.4, the 3, and the 5 are independent of each other, so let's assume they're, you know, say statistical, systematic, and I don't know, luminosity or something, then you could add them in quadrature and perform things that way. The more professional way is to construct individual covariance matrices for these different error sources, sum the covariance matrices, and then you work with the inverse of the sum, not the sum of the inverses, okay? But personally, I have problems with that, and it does lead to perverse results in some circumstances. From Pranjal, last comment, Pranjal writes that, also I've heard a lot about priors being important in statistical analysis. Yeah, can I expand on where it becomes important? So a prior, Pranjal, a prior refers to a Bayesian treatment, which I have not mentioned at all, I think only in passing at one point. Unfortunately, I don't think I'll be able to lecture on it tomorrow unless I really cut back the discussion of hypothesis testing. So tell you what, Pranjal, rather than giving you a nothing answer now, let me see if I can work in 3 or 4 slides concerning Bayesian methods in this kind of situation, because they're becoming more important. I know people in neutrino physics are beginning to use these things, and I can then try to give you an answer. But basically, when I lecture at Northwestern on statistical methods, I spend a whole week or 2 talking about that question. So it's hard for me to give you a 1-minute answer. Sorry. Okay.
Okay, so I think we should thank Michael virtually, and he has to come back in about 20 minutes for the discussion. And so hopefully everybody can stretch and walk around for a little bit and show up for the discussions according to the rule that Ethan set up. And I think Michael will start on room E.
Yeah.
And Donna will be in room U. And then you guys are going to switch. We haven't figured out how to tell you that you're supposed to switch, but I'm sure we'll have it figured out in the next 20 minutes.
Well, it's, isn't it 15 minutes plus 15 minutes?
I don't remember. Ethan can say more.
Okay. All right. Well, I'll start out in the electron channel first anyway. So thank you everybody for the questions. I really love the feedback from all you guys. See you soon.